In this lecture, we are going to start the main subject matter, multivariate optimization. Okay, so first consider the fundamental ideas. The definitions and optimality conditions go very much in line with what we did in single variable optimization, except that the definitions and everything is in multivariate space. Okay, so for a scalar function of a vector variable, n-dimensional vector variable, you will call a point x star as a local minimum point or relative minimum point if there is a little epsilon neighborhood around it in which the function value at the current point is less than equal to the function value at all other points. So in this little ball around x star, okay, with radius epsilon, at every point the function value is either higher or equal. In that case, the current point x star will be called a minimum point. Basically, it means that x star has an epsilon neighborhood, some neighborhood in which there is no other point which is better than this, okay, where the function value is lower. So as we did in single variable case, these three extensions will follow that if here strict inequality holds, then we will call it a strict local minimum. And if this holds for all epsilon, all positive epsilon, whatever large it is, then we will call it a global minimum point. Okay. And again, if it holds for all epsilon in the inequality, strict inequality, then you will call it a strict global minimum, right? And all these definitions with the inequality reversed will give you the definitions for maxima. Now, as in the case of single variable problems, if the function is differentiable, then derivatives will give more concise and easily verifiable conditions. And again, we go to Taylor series, but here the Taylor series is for multivariate function. So here, rather than f prime, you have gradient transpose delta x. Okay. So since gradient is a column vector, you have to do transpose to have this product, inner product basically, plus the second order term, plus higher order terms will be there. So as long as this vector, the gradient, is non-zero, as long as any component of it is non-zero, you will find some delta x directions, some delta x vectors for which the function will increase, and some other delta x for which it will decrease. So if it increases for some delta x, then for the negative delta x, it will decrease. Now, if delta x is small enough, then this term typically will dominate all other terms. And that is why it will not matter then what the others are, right? So for a minimum or maximum for that matter, it is very necessary that this term is zero. And for that, this entire vector has to be zero because delta x can be in any direction. So that is the first order necessary condition, without which you cannot even talk of extrema. Now, if this is zero, this vector, entire gradient is zero, del f by del x1, del f by del x2, all of them are individually zero, then this term vanishes. The moment this term vanishes, the series will be dominated by the second order term. And the good thing about the second order term is that its sign can be one way because there is one delta x on this side and the delta x is on that side. So if for some delta x, this term is positive, then for exactly the negative delta x also, it will be positive. Okay. So the second order term dominates the series and its eigenstructure will come into play. That is, how are its eigenvalues. So here in the case of single variable problem, we had half second order derivative into delta x square. So there we talked of the second order derivative being positive, okay, for minimum. So here we will not be able to talk about this being positive or negative or positive or zero or whatever. But we will be talking about the matrix being positive semi-definite and positive definite. For the necessary condition, we have positive semi-definite. That is, now necessary condition is expressed in this manner. If x star is a local minimum point, then these things are necessary. That is, without these two holding, it cannot be a local minimum point. It cannot be a minimum point. Okay. On the other hand, if it is not positive semi-definite, then rather positive definite, then that will be sufficient. Okay? That's not necessary, but that will be sufficient. So you will say the sufficient condition in this manner. If the gradient is 0 and the Hessian is positive definite, then x star is a local minimum point. Then we know. Okay. Now, what are the other eigenstructures possible between, other than positive semi-definite, positive definite? There are a lot of other eigenstructures for Hessian possible. So let us quickly have a look at them. If the eigenvalues are all positive, then the Hessian is positive definite, and in that case, it is a minimum point with this condition holding anyway. Okay, so if the first order derivative, the gradient is 0, then it is a stationary point, and here in this table we are talking about only stationary points. So if all eigenvalues are positive, that means in all directions the function increases on both sides, this side as well as that side. Okay, so overall the function profile will be like this. So it will be a minimum point at that point where the gradient is 0. If it is all negative, then that means that from the current point in all directions the function value will go down like this. Okay, and therefore the current point where the gradient is 0 is a maximum. These two cases are obvious. If the eigenvalues are some of them positive, some negative, and maybe some 0 also, in that case you call the matrix as indefinite, and in that case it's called a saddle point, because the direction, the eigenvector corresponding to which the eigenvalue is positive, there the function will increase in all directions like this. On the other hand, in another direction along which, that is another eigenvector, for example, for which the eigenvalue is negative, then around that, in that direction on both sides the function value will decrease like this. Okay, so in some directions it is increasing, in some directions it will show a minimum, in some other directions it will show a maximum, and that is why it is called a saddle point, because saddle literally means the back of the horse where you sit when you ride it, and on the back of the horse, how is the shape? From the tail to the head, the saddle point is a minimum. On the other hand, from left to right, it is a maximum. Okay, so that shape is called saddle. Okay, so in the case of indefinite Hessian, in which some eigenvalues are positive, some negative, you have a condition of saddle point. And in that case, whether some are 0 also, you don't bother about that. Now what is left? These two situations are left. Some of the eigenvalues are 0 and others are positive. So only non-negative, okay, positive or zero. So in that case, the maximum, the eigen Hessian is called positive semi-definite. The matrix with this kind of nature is called positive semi-definite, and it is singular. Why I mention singular especially? Because when you say positive semi-definite, you simply say that eigenvalues are supposed to be positive or zero. You don't insist that some of them have to be zero. Okay. So if some of the eigenvalues happen to be really zero, then the matrix is singular also. Okay. And in that case, it may be a minimum. That is, the necessary condition for a minimum, but not sufficient. Similarly, some zero, others negative will give you a singular Hessian, negative semi-definite, and in that case, the X star point may be a maximum, may not be. Now, in these two situations, we cannot resolve it within second order analysis. So in the case of single variable problems, we conducted third order, higher order analysis to draw appropriate conclusions. Such a thing in multivariate problems will not be so easy, but in principle it can be done. If you are adamant that you will get it with derivatives, you will resolve it, then you can do it. The way to handle it is to consider the null vectors of the Hessian. That is singular, so it will have some null vector, null space. So those null vectors have to be analyzed in more detail. How? So suppose x star is a stationary point, gradient is zero, and the Hessian is symmetric, so it can be diagonalized with an orthogonal similarity transformation. And since it is positive semi-definite, so all eigenvalues will be non-negative. So suppose the Hessian is diagonalized through orthogonal V with eigenvalues like this. R of them positive and the rest are zero. Positive semi-definite, some positive, some zero. So these are positive. R is the rank of the matrix and the rest are zero. Then you can have a coordinate transformation in which you basically change your variables from x to y. That is, around this current point x star, which we are analyzing, you basically make a shift of the coordinate axis and a rotation also. So the shift is effected through this and rotation through v. Okay, and then x star is already in hand, v is already determined based on the Hessian at x star. So what remains is y. So y is of the same dimension as x. Okay. So, but now it is a function of y. So call it phi of y. Now the variation of the function around x star. If you want to study that, then you fix x star because you know that, v because you have determined that, and now around x star you change x. So basically y changes. Okay, and when you change y by one coordinate at a time, then x basically changes along the eigenvectors of the Hessian matrix. Okay, so if you consider the variation of fx around x star by considering variation of phi y, so phi 0 is 0, phi 0 is fx star, and grad phi 0 is 0. That we already know. So grad phi y is differentiate this with respect to y. How to do that? Grad f will be multiplied with v transpose. This is basically the chain rule. Okay. So v transpose grad f at this point. So when you put y equal to 0, you get V transpose grad f x star. And grad f x star is 0 anyway. So this is 0. Hessian of phi. So there you will again have, this is constant matrix, so stays as it is. And this gets further differentiated. So you get the Hessian into this V. Okay. So now again, if you evaluate at y equal to 0, then you will get V transpose HF x star V. And since V is the orthogonal diagonalization, V gives the orthogonal diagonalization of the Hessian. So V transpose HF V will be diagonal, and that is this matrix. Okay. So phi y will basically be phi 0, that is fx star, plus the first order change, which is 0 because of this, plus the second order change, which is half delta y transpose this diagonal matrix into delta y, or y rather, half y transpose this diagonal matrix into y. So since it is diagonal matrix, so the second order term will turn out to be like this. And only first R of them are useful. Rest of them have zero term as lambda k. Okay, so keep these and terms of degree 3 and higher. And now we know that lambda 1 to lambda k are positive. Lambda 1 to lambda r are positive. So all these are positive. We don't know about them, about these. Okay, but then for k equal to 1 to r, these will not matter. Okay, because along those directions anyway this is positive and this is dominating for small y. So in the subspace of the first r eigenvectors, x star is a minimum. In all of those r directions, you will have this kind of a profile of the function. Okay, for the others, you have to then consider the third order, fourth order derivatives the way you did it in the case of single variable optimization problems. Okay, exactly like that. So now you do not need to bother about the derivatives with respect to the first r coordinates of y, only the rest, and in that also individual only. Okay, so only the direct second derivatives, no del 2 phi y del y k del y j, no, nothing, no cross derivatives, only the direct single direction third order, fourth order derivatives will give you the diagnosis as in the single variable case. Okay, so this you can do, but very rarely one does. So this is more or less what we had to discuss in this lecture, and beyond this I will just raise two of the operational issues which are important as we go further. So one of them is contour plots. Before contours, we talk of level surfaces. For a multivariate function fx, the surface on which at every point the function has the same value, such a surface is called a level surface. Okay? So the set of points in n-dimensional solution space for which the function value is same is a level surface. So it's level, you see. So for every distinct function value in the interval from minimum to maximum, we have a level surface of the function. And a level surface for a particular value need not be all connected in one surface. It may be two surfaces like this. Okay? That's possible. What is important is that level surfaces corresponding to two distinct values of the function will never cross, never touch. Important and obvious actually, because if two of them touch or make a contact, intersect, then at that point you will not know whether the function has this value or that value. Okay, so that's not possible. Okay, so the way you see streamlines don't meet, electric lines of force don't meet, like that level surfaces don't meet. Okay, now in 2D, if you insist on the function value fx equal to some given value, then you do not have two variables free, because that is an equation in two variables. So basically, in place of level surfaces, then you will have level curves, which are called contours. And contours are well known, very famous for a long time, and have been used in cartographic depictions. So, over a hilly terrain or in the ocean, all the points which have the same height or the same depth connected together give you a contour curve. So here also the meaning is same. If you take particular objective function value and all those points in the 2D space which have that same particular value of the function, you connect them and get a continuous curve, or more than one continuous curves. Those are contours. So for one function value, you get a contour, one curve or more curves. For another function value, you get one or more. For another function value, you get one or more, and so on. Okay. So, and with all of those curves plotted on the single set of axes, what you get is a contour plot. That helps you to visualize the way the function behaves, the entire function profile over the entire domain in which you are interested. Okay. Now, this is possible, this plotting and visualizing is possible only in two variable functions, because 3D plots cannot be viewed with that clarity. And for high dimensional functions, you don't really know how to plot them appropriately. Okay. So, how a contour plot is made? The procedure is that first of all, you choose a rectangular domain in the x1 x2 plane in which you are interested in the contour, and decide on a grid on it. That is, the x1 coordinate, small steps, x2 coordinate also small steps. So basically, a grid of points you have got on that rectangular domain. And for the function, then you decide on the function values f1, f2, for which you want those plots, those curves. Okay. Now at the grid points, you evaluate the function simply, and you have got a matrix of function values at those grid points. Now you can interpolate these grid values to find out at which precise point the function has value f1 or f2 or f3 and so on. And you can tabulate them separately. That is, these are the points with f1 values, these are the points with f2 values. The grid points themselves may not have exactly f1 or exactly f2, but nearby values, from that you can interpolate and get the precise internal points of a grid of a scale cell where the value is precisely f1, precisely f2 quite accurately. And you list out those points separately. Points with function value f1, points with function value f2, and so on. Okay. And then you connect the points in each list in appropriate order so that they show you a continuous curve. If necessary, by further interpolation, you can get intermediate points also. Now, plot all these curves, curves for f1, curves for f2, curves for f3, with annotations f1 value, f2 value, etc. on the same plot, and you have got a contour plot. Now, this is a lot of work. You will not agree to do it. But the good news, which you know perhaps, is that most plotting software, whether you use for plotting MATLAB or GNU plot or whatever, give you some facility, some you know uh, tool to make contour plots. You have to give the minimal data. Basically, you have to give what you want. That is, you have to describe the function, for which function you want the contour plots, and you have to give the function values, maybe some 9 of them or 30 of them, okay, and the grid in which you want the contour plot. By only specifying this, which is what you want, most plotting software will give you appropriate contour plots. But how to give it to the plotting software? For that, you need some practice. And I advise you that you, whatever is your favorite software for plotting, in that you find out and experiment and try to plot a few two variable functions and see how they look. And this will help you in analyzing the performance of methods on problems. Okay? And also it will show inside out of the functions and optimization problems. It will show the function, it will show the way the algorithm progresses, and when we come to constraint optimization problem, the function constraints and the progress of the algorithm all together you can visualize well in that. Okay, so you should have some ability, some practice of drawing contour plots whenever you want. Of course, you can't do it in exams, but for your background study and for assignments, etc., you can do it. Or the take home kind of tasks, term papers, you can do it. So, how, what kind of features we get in contour plots? A minimum or maximum point typically is enclosed by shells of closed contour curves of continuously increasing or decreasing function values. Like if the function value at the minimum point is 3.2, then just around that there will be a around that point there will be a closed contour of value 3.3, then around that 3.4. In fact, between 3.2 and 3.3 also, if you want, you can get 3.25 or whatever, 3.23. Okay, so after outside 3.2, you will have a little shell 3.3, enclosing which you will have another function 3.4, another curve, another contour curve, around that 3.5. And after that, the shells may not remain as closed. I mean, they might keep on changing their shapes, and even some of them might be open. Okay, so but just around the minimum point, because of the continuity of the function, for some time, some zone that enclosed shells, that feature you will find, and the shapes etc. of minimum and maximum will be the same. Okay, and that is why unless the function values are given, you will not know whether you are seeing the contours of a, unless the function values are given, you will not know whether you are seeing the contours of a hill or a sea. Okay, whether these are heights and or depths, you will not know. So those things you know by the annotations of the function values on those contour curves. Okay, so only through the function values you recognize a minimum point from a maximum point. Otherwise, they look same. It's a saddle point which is the most interesting in the contour. Okay, contour plots. Now, you may or may not have specified the value of the function at the saddle point in your list of function values for which you want the contours. Now, if you have supplied that as one of the function values precisely, then through that you will find two intersecting contours with the same function value. Okay, that particular contour will appear as a pair of curves intersecting at the saddle point. Now, most of the time you don't know that precise value of the function at the saddle point, so that would be missed. But below that, there may be a function value for which you have asked for the contour, and above that, there may be another. Okay. So typically, in that case, around the saddle point, one pair of contour curves will come across like this, okay, facing each other on the convex side, and another pair may come like this. They also between them will face on the convex side. Okay. So even if the mutually intersecting two curves with the same function value you do not find, simply because the saddle point value has not been mentioned in the list of f1, f2, f3, etc. If you find four contour curves coming from four sides and facing one another with their convex sides, then you know that there is a saddle point there in between. Where if you give fine values in between, then you will get it. Okay. So along one pair of these, the function value will be the just higher one. Along the other pair, on the other pair of contour curves, it will be the just lower value than the saddle point. In between, there will be some value of the function for which you will get two intersecting curves. Okay. So the saddle point then marks a maximum in one direction with the function decreasing on both sides, and a minimum in another direction with the function value increasing on both sides. See a schematic. Say there is a maximum here at function value 7, which we will not see actually because one point will not show up in the contour. Around that, this curve will show up with function value say 6. After that, function value 5. One contour curve like this, another contour curve like this. Beyond this rectangular domain, we don't know whether this will loop and come back, whether this will loop and come back, we don't know because we have not done it, we have not seen it. And after that, decreasing function values for 4, for 3 separate contour curves. On this side also, 4, 3, and then you see this contour curve for function value 3 and this also for function value 3 are facing each other, form a pair like this. Okay. And here this one with function value 1 and this one function value 1, they are also facing each other in a pair. So this zone is seeing four contour curves on four sides. Okay. On opposite pairs, on one opposite pair it is a higher function value, on the other opposite pair it is a lower function value, and that shows you that here somewhere there will be a saddle point with some function value between 1 and 3. I have shown it with 2 and like this, separating these two and these two, and another intersecting contour curve with the same function value, separating these two on one side and these two one side on the other side. So these two intersecting curves together separate out these four zones. Okay? So this is a typical feature of a saddle point. Okay, and you see now if from this minimum at function value -4, if you start traveling towards this minimum function value -1, then the function value will increase 0, 1, 2, 1. So along this curve, at this point, there will be a maximum. On the other hand, if you travel from this contour curve to this contour curve, then you will find a curve along which this will be a minimum. So if you travel from this contour curve 3 to this contour curve 3 through some other path also, you will find a minimum, but there, if you do not cross this, then at the same time, it will not be the maximum on the other direction. Okay? So at the saddle point, it happens that this direction giving a maximum point and this direction giving a minimum point come together. And that is the situation of the saddle point. That's a stationary point. First order derivative is zero. And the second order derivative along this eigenvector is negative. Along this eigenvector, it is positive. So at saddle point, the Hessian is indefinite. Okay. Now, contour plots was one of the topics which we needed to discuss in this lecture. Another is numerical differentiation, the process and the cost. Because several optimization algorithms use derivatives, and there are situations where the objective function is differentiable, but you cannot have straightforward expressions for the derivative. In that case, you need to evaluate the function at neighboring points, and from finite differencing, you have to find the numerical derivative. Okay. So now you might need to compare one algorithm which does not use derivatives and another algorithm which does together. So how will you compare the computational cost? So for every derivative evaluation, gradient evaluation, you have to work out the corresponding number of function evaluations with which you can develop the numerical derivative. Okay. And there are two major methods of numerical differentiation. One is by the forward difference formula, and the other is by central difference formula. Okay. Central difference formula give you more accurate derivative estimates, but they are numerical, computationally costlier. In comparison, forward difference formula requires less function evaluation, but the accuracy is also less. Trade-off. So these are the forward difference formula. For gradient, with a selected small number, to evaluate the gradient at fx, you change one coordinate at a time by a little number delta, okay, and evaluate the function at a neighboring point. Then the difference of the function values you divide by delta. That is standard derivative. Okay, so for developing the for estimating the gradient, you will need to do it n times for n directions, right? This you have already got because the function value you have already got. So additional n function evaluations you have to know, you have to determine to get the gradient completely. This calculation is nothing. It is the function evaluation at the additional points which is the issue. For Hessian, these are the formulae, and this you will already have function values, and this also you have because you have determined the gradient. So this will be the new. For the second derivatives of this type, the cross derivatives basically, which will form the off diagonal terms in the Hessian matrix, you will have this. Okay, so diagonally away, change in both coordinates I and j, minus this, and plus the current function value. So basically, this formula you can get by using one formula in the EI direction and the formula in the EJ direction. You subtract those two and then divide by another delta. Okay, so then you'll get this. So for after grade gradient, this will require n values here and nn minus 1 by 2 values here. These ones are already known. Okay, so after gradient, these many extra function evaluations you have to make. Okay. Similar expressions you can have for central difference. So for central difference, the gradient, the derivative, does not need the function value at the current point. It needs one on the other this side, one on the other side. That is how it is central. And therefore the division is by 2 delta because difference between these two is 2 delta. Okay. But this is how it is costly. It will require 2n additional function evaluations, okay, rather than n. in forward difference. However, these two additional function evaluations which you have made for gradient, the same ones will be useful in the diagonal terms of the Hessian also. So this will need nothing more, okay, other than what you have done already here. However, the cross derivatives will need all four new, because none of these four have been used in the function or the gradient. So basically the further function evaluations will be these many after gradient. So this is costlier than forward difference formulae, okay, but more accurate for the same delta. If you decrease delta, then the forward method will start competing again. So for the same delta, central difference formula will be more accurate but more costly. Okay. So in this lecture, what we have covered, first, the extrema of multivariate functions. We saw their optimality conditions. We defined them and saw their optimality conditions, which are similar to univariate optimization. And the difference from univariate functions comes in the other two things that we did. One is that two variable functions cannot be shown in a simple graph of x versus f, but it can be shown in contour plots, and there it has an advantage over multivariate functions. Okay, more than two variables. And the multivariate functions, whether two or more, in that case, the numerical differentiation is a costly affair, is an issue. And for that, you need to know correct formula and you need to know the cost to know how much computational effort you will need to spend to conduct every fresh iteration of a method. Okay. So after this, in the next lecture onwards, we will start studying methods of multivariate optimization. First, the direct methods which do not use derivatives. Okay. So here we stop, and in the next lecture we will meet with direct methods of multivariate optimization. Thank you.